Right, relax. Good afternoon. Welcome to Unicourse. This afternoon, we're looking at Unit 22, Electronic Circuits and Devices, and we're going to be looking at the Assignment 3, the theory, hints and tips at the end of this presentation. So let's look at what we'll be seeing through this presentation. We're going to be looking at the different types of oscillators and their applications. We'll be assessing their performance characteristics of types of oscillators, analyze results obtained from applying practical and virtual tests on the oscillator needs. So an overview of the assignment brief. The first pass question, we'll be looking at examining types of oscillators. You'll be using the study guides, further research. I want you to identify different types of oscillators available. And the next one, on the merit one, is to assess the performance characteristics. So this one we'll be looking at a simulator, building the circuit and testing it. And the final one, if you are working through to the distinction one, is to look at the results of the virtual one, build one up on breadboard and compare the two and make some recommendations on the virtual one and the real one. So oscillators. Now, oscillators have been around a long time. I can remember using them back in the 1970s, but they were used right to the turn of the century to develop radio transmitters. And some of the oscillators we're looking at today were actually similar designs used about 100 years ago. So what is an oscillator? The device repeats AC. It doesn't produce DC, it will produce an AC signal, but we use a DC supply to get the oscillator to work. Now, the output of the oscillator can vary, and we'll be looking at that in a minute. And that is going to be determined by the design and the component choices. The amplitude is typically constant, but the frequency can be altered. Can be altered as well, but usually what will happen is that when we design the circuit, the amplitude will stay the same, but we can actually vary the frequency. Here's a block diagram of one. So what you've got is you've got the oscillator circuitry, which is various components, including capacitors and resistors or a crystal. You could have an amplifier, but sometimes they are self-contained, the oscillator. Amplifier which could actually be built into the actual circuit as well. But what makes this an oscillator is that the output, which is this point here, is fed back through a little network back to the beginning of the oscillator, and that will keep going round and round, and that causes the oscillation effect. Now, the waveforms we have usually classed into three different types. What we have here is the sine wave, which is here on the left. Then we have a square wave, and then we have the zigzag one, which is a sawtooth or triangle. Well, this one looks more like a sawtooth. So, sine wave and the relaxation oscillator, which will produce a rectangular waveform, and the oscillator produces a sawtooth. And we call this the sweep oscillator. Many years ago, when we built TVs, we used to use it as part of sweeping across the screen, but that's no longer used. But each of these three are used in different types of electronics. The ones that we usually are familiar with is the sine wave, which is usually used on the audio side. The pulse one is usually used in digital. It can actually be used as part of a clock and various other types of digital circuits. So let's look at a sine wave oscillator. And as I said before, they used to be using transmitters, but they usually use radio audio frequencies. And we need a DC supply to get these to work. Now, this one here to our right is a 555 timer, but the output of this one won't be a sine wave, will be a square wave. And we've seen these used in where we're using clocking circuits, where we want to get a clocking frequency. Very stable, quite easy to build, and you don't have many components. And generally, the components that will alter the frequency are these resistors and this capacitor. And this allows us to feed an output here. There's no input, just pure input here, set by a certain voltage. And the 555 timer, a very common one. Now, the oscillators, common ones, which have been around a long time, are the Hartleys, the Colpitts, RC ladder. And we'll be looking at these different oscillators and looking at the circuits and briefly looking at how they actually work. And the crystal one, the crystal sine wave oscillator. Now, the Wien Bridge is a very, very popular one, and that one's used a lot in test equipment, and it's used there to produce a multiple type of sine waves, square waves for the testing equipment. It has a phase shift in the input as well as controlling the frequency. Very stable. As we know, there's no input signal, and we'll look at that very shortly. So let's look at the circuit. So here we have a Wien Bridge oscillator, and the frequency is usually the capacitor and the resistor. There's a feedback circuit, as we just right in the first block diagram. It's fed back here, and usually the signal produced on an oscilloscope is very clean. And here one is a sine wave, and by altering the capacitors or the capacitor and the resistor, you can change the frequency. And in the quite the old style generators or signal generators that were used by engineers for testing audio equipment, TVs and radios and stuff like that, what you would have is that you have a group of either discrete transistors, or if it was a bit later on, using an op amp, and you can set different frequencies. You can have a range from about 50 hertz up to a few megahertz. So they're quite a stable circuit. The LC coupling oscillator. Now, this is a Hartley oscillator. This center one here, we call it a tank. And this will determine the actual frequency. Now, in the good old days, we used to have a valve connector up over here, but now in recent years, it's a transistor. But we don't see many of these circuits. It looks, if you took out this, it just looks like a little one-stage amplifier. But what it is you connect up the collector through these two coils, which are set, which you designed it, and they resonate with the capacitor, and you use this for a tune frequency. And these sort of circuits, in the old days, was used as transmitters as part of the transmission side. So if you wanted to produce an amplitude modulated signal, you may use something like this. The output is fed from the collector, and the circuit you can see is what is known as a tap coil, because we've got this capacitor which connects up to R3. And it's known as the Hartley oscillator. And this circuit here is a tank circuit. Problem with this sort of circuit is it's difficult to tune. And when you're using it for a radio frequency, an RF transmitter, you want something which is quite stable. But it does work. The L1 and L2, very cool, and it's a bit fiddly to set up. I've tried one of these years ago. Not too easy to set up the right frequency. So this is the basic circuit. Let's look at the next one, the Colpitts oscillator. Now, instead of having two coils, we're having two capacitors. And I've always remembered it. How do you remember between the Colpitts and the Hartleys? We remember C and Colpitts, and that's a Colpitts oscillator. Same it's fed into the collector of this little one-stage amplifier, and instead of actually tapping the coil, you tap the capacitor. And it's quite a stable little circuit, and was used, and I've used them years ago as part of a little radio transmitter. What quite often we did is it produced an RF frequency, but we couldn't really apply audio to it. So what we used it for was using what was known as Morse, so we could link into the actual RF side of it, and then we can send out more signals. So as I say, it uses two capacitors in part of the tank circuit, and this eliminates the self-inductance. As we know, inductance is coil, so it makes it a lot more stable. And it's a simpler design. It's easy to build because with only one coil, you've not got a problem with the wires. The capacitors are probably easy to do. The only thing is you've got to get the right tolerance, so you have to design the circuit in such a way that you can work out the right frequency. And that's known as Colpitts. Works nice at higher frequencies, and there's a low impedance path for the capacitors, which was more accurate sine waves. Now, the crystal oscillator, that is the superior one. The reason why is because the crystal is very stable. Now, you can see where we've got the crystal, which is going across here, these inductors, and you can vary the capacitor here to change the frequency. But the crystal oscillator, which I can remember using in the 1970s, it would give you a fixed frequency, and you could actually change it. But one main advantage of the crystal over the Colpitts and over the Hartleys, that the fact that the frequency was stable. What we did is we actually chose the actual crystal frequency, which you used to buy, and then that we put into the circuit, so you didn't have to do anything, as long as you got the right values of resistors here for the part of the circuit here. Now we notice on this one here, it's not coming, the output is not coming onto the collector, so there won't be any amplification. It'll be unity gain, but it's a bit like a buffer circuit, common emitter stage. But as you can see here, you get a nice output. Now on this one here, we've got it connected, tapped at the coil, right back to the emitter here. That's another stable circuit. And here to the right, just give you an idea of how the circuit will look. But let's say we've got the tank circuits on the top here, always on the collector. And let's say they're quite a stable, nice little circuit to build, and they're quite easy as well to construct. So it's a piece of quartz crystal, which is a piezoelectric device. The device bends and produces a mechanical stress which is subjected to the voltage, and therefore we can create this frequency. So that is the circuits, but we don't often see them now. We used to see them probably early on in computers where they wanted to use a very stable frequency, the clocking frequency. So you see a little crystal built circuit. But a lot of them are using a chip where it's all embedded into the chip with the circuitry. The RC ladder. Now this is another one here, which we see onto our right. And by changing the RC, you'll get this 180-degree out of phase and the output. Also used as a function generator as well. And when you design the circuit, you're going to make sure that the capacitors and resistors are all equal. Otherwise, application will not even, it won't work the circuit. And as you can see the output here. Yet again, this has got through the feedback here, through this little amplifier here, which is the common emitter stage. And the output is connected up through, you've got RL here, and then you've got the tapped off here, and you get some form of amplification of it as well. But you're only amplifying the signal from the start here, depending what sort of transistor and what configuration you have with the RL resistor, with the load resistor. Here's another version, which is the Twin T. Quite a simple circuit, very different configuration to what we've seen before, and it's a very reliable oscillator. And it doesn't require any negative resistance to stabilize the system. And it's resistant to any distortion as well. So when you get a clear sine wave sort of output. Here we're moving on now to using the op amps. What was traditionally used some years ago were things like the 741s, as you can see here, the negative and the positive supply voltage. And here we've got the output here, instead of getting a sine wave, and this one you can see on the trace here is a square wave. And depending on the value of the resistance and the capacitor, will allow you to give you a different frequency. And this will also generate a tone as well. Binary signal from the communications and electronics, but as the saying goes, it's more, I wouldn't use it in RF work, it's probably using more in computer stuff. And this sort of thing can be used as a pulsing to be used for some form of emergency services where you get these lights where you need to flash off and on. And the clue here that you will have in your assignment 4, there will be a circuit which you need to build which requires the LEDs to flash. So now we've got this astable circuit. This is using the 555. We've got 2 waveforms here. And the reason why I have 2 waveforms, depending where you have the look at which part of the output. So you've got the output over here, which will give you a nice clean square wave. If you don't get a clean square wave, then you've got something wrong with your circuits, or the chip's not properly in properly, or you haven't got the right grounding. And then you've got this sawtooth effect, and that is at the capacitor. So that is probably at the, you get this at the capacitor. By checking it through, you can see the 2 forms. We'll look at a circuit similar to this a bit later on in this presentation. So the 555 timer is a very simple circuit to build. They're quite cheap to get hold of. They're quite a stable circuit once it's built correctly to use as an oscillator. Now, when you are building circuits, I just want to briefly touch on this. Here we can see here, we've got this dimple here, and when you are building a circuit, constructing the hardware onto breadboard, what is very, very important that you've got the right connection. So you've got here pin 1, which is ground, and pin 8 is VCC. So very important, because if you have the wrong polarity, there's a good chance that you can actually damage the chip and it may not work. And the rest of it is not too bad if you are connected wrongly, but I can't vouch for it. But generally speaking, as long as you supply VCC and the ground's connected up correctly, there shouldn't be a problem. So that is just explaining, and you can go through this in your own time in the video again, looking at it, and tells you exactly what each is. And we'll look at the configuration, i.e. the components that are connected up to this chip. So let us now look at performance of the oscillator. Now, part of this assignment, you will need to construct the circuit that's actually come with the assignment using a simulator. So we're going to look at a couple of simulators, just an overview of it. Here we've got the TINA T1, and here we've got the circuit to our left. Now you'll notice that once the circuit is switched on, you don't get an instantaneous waveform. It takes time, and the software, you can see this going here, and then you'll see this nice sawtooth effect. And then if we look at another one, this is using Circuit Lab. So that one probably will be quicker. When you put a simulator on, we can look at the outputs, which is either the square wave or the triangle wave, and you can set it up so you can actually look at different points on the circuit. There's quite a lot of sample circuits in Circuit Lab, and it's one I have been recommended for the last 12 months. And here we have Circuit Wizard, and this one here is circuit, and there you can see the waveform outputs as well, and that will come up in real time. You can see 2 waveforms because it's got a dual oscilloscope, and on the right usually there's a way that you can change the timing of it to either increase the length of each of the squares or the triangle as well. Now, if you are going to build the circuit, what you'll need to do is you need to build a breadboard. And what I've done here is I've got some examples of the actual circuit built on the breadboard and also the waveforms. So you can see here that the circuit is built nice, neatly. The cables are all connected up, and we've got the chip in the middle there, the 741. We can't see where the DC supply is, but there's a DC supply, and we can't see the test instrument. And this is a screenshot of the waveform that was produced. So these are the things you have to do. You need to carefully follow the circuit diagram. You need to ensure that the IC is in first. So what I would suggest you do is you put the IC in first into a circuit, check for the 0 volts and for the supply voltage. They are the key ones that you need to make sure you got the right thing. One is that you need to have the right polarities, and two, you are making connection. So you need to ensure that you've the wire enough to drop the wire into the breadboard inside those holes. Once you built the circuit, don't switch it on. Check the constructed circuit. Look around it. Make sure all the wires. You may just go away for it for a few minutes and then come back to it, because sometimes if you're building a bigger circuit, there's lots of wires, resistors, and capacitors. This one's not the one you're building for this assignment. I said check the positive and negative connections to our DC battery or the bench supply. Okay, so we're nearly halfway. We've got more than halfway. Well, what we're going to do now is we're just going to look at the key points in completing this assignment successfully. So the first thing you need to do is explain 3 different classifications of oscillators. Now, what you've got is the Unicourse guide notes. There's quite a lot of circuits, oscillators there with explanation. What I suggest is look at that, but also I recommend, or I highly recommend, is reading and look at various other circuits and do some comparisons. Now, if you are using either the circuit from Unicourse or using it from the website, what I suggest you do is you take a screenshot from it, put it into paper, and re-annotate it, and also put your own words and reference it where you've actually got it from. So there's quite a lot around for oscillators. It's quite a well discussed topic, and there's quite a lot of sites to look at. If you've got any problems, just give me a ring or email me, and I'll guide you to where you can find other sites to go to for further reading. Make sure that all the circuit diagrams are annotated, including the waveforms. Very important. And assessing an oscillator circuit using a circuit simulator. So you've got various ones here. You can use Tina, you can use MicroCap. I think on this one here, it's using the Circuit Lab. Now, you photographing your practical. So the first stage is make sure the kit is all set out. And this one here, we can see the function generator to the left. We can see the oscilloscope to the right, and we can see the breadboard here. Now, what you can do is you can show an overview of it, and you can actually annotate it all: function generator, oscilloscope, and breadboard. And then if you want to, take just a screenshot of the waveform and put that in separately within your assignment evidence. But annotating it does give it some more clarification, and it'll support any of your written text. So I'll let you have a look at that one for a few minutes. Here we're looking close to the breadboard. You can see here what a chip. It's not the same circuit as the one you'll be building, but you can see where it's been set up, and you've got in the center there where there's no connections, and the resistors are at the bottom here, and you connect up the power supply at the top there, which could be your top rail there, and your negative rail at the bottom here through this rail over here. So various circuits, study guides and further reading, annotate your diagrams, explanation of how the circuit works, input and output waveforms. In your case, for the oscillator, it's just generally output waveforms, but there is one circuit where you can look at two waveforms, which I mentioned earlier. I think one was the you'll see a connected to a capacitor, which you get a sawtooth and you get a square wave. Part of the referencing is important, which you need to reference it within the assignment, and then you've got all the information right at the bottom of your assignment evidence. Also, all the assignments now, barring any mathematic ones, but the ones that for this unit 22, the only thing that you can sketch by hand is the circuit diagrams. The actual written evidence has to be typed up. That's the new assignment brief. Okay, thank you very much.